In 1901, this ancient Greek artifact was discovered in a shipwreck off the island of Antikythera. 3D X-ray scans have revealed it contains 37 interlocking bronze gears, allowing it to model the motions of the sun and moon and predict eclipses decades in advance. Constructed around 100 or 200 BC, the Antikythera mechanism represents a sophisticated early computer, the likes of which would not be seen again for at least 1,000 years. Now, of course, this computer didn't work like modern digital computers. It works by analogy. The gears were constructed in such a way that the motions of certain dials are analogous to the motion of the sun and moon. It is an analog computer. Here is a simple analog computer for adding two numbers together. If you turn the black wheel some amount, and then turn this white wheel a different amount, the gray wheel shows the sum of the two rotations. In contrast, this is a digital mechanical computer where you can add two single-bit numbers. So 0 plus 0 equals 0, 0 plus 1 equals 1, and 1 plus 1 equals 2. These two devices illustrate the differences between analog and digital computers. Analog computers have a continuous range of inputs and outputs, whereas digital only works with discrete values. With analog computers, the quantities of interest are actually represented by something physical, like the amount a wheel has turned, whereas digital computers work on symbols, like zeros and ones. If the answer is, say, 2, there is nothing in the computer that is twice as much as a 1. In analog computers, there is. For thousands of years, people used analog devices like the Antikythera mechanism or slide rules alongside digital devices like abacuses. And up until the 1960s, the most powerful computers on the planet were actually analog. Digital computers exploded onto the scene with the advent of solid-state transistors. And now almost everything is digital. Most people have never even heard of analog computers. But today, that may all be changing. Moore's law, the idea that you can double the number of transistors on a chip every 2 years, it's reaching its limit because transistors are nearly the same size as atoms. Simultaneously, advancements in machine learning are straining the capabilities of digital computers. The solution to these challenges may well be a new generation of analog computers. One of the most important problems humans have faced for millennia is predicting the tides. Napoleon and his men nearly died crossing the Red Sea due to a miscalculation of the rising tide. And sailors routinely needed to know the tides to bring their ships into port without running aground. Most coastal locations on Earth experience too high and too low tides per day, but their exact timing varies, as does their magnitude. And this is partly caused by local factors like the depth of the seabed and the shape of the shoreline. In the late 1700s, to describe the tidal flow of the oceans, Pierre-Simon Laplace derived a set of complicated differential equations. They had no analytical solution, so at the time they were basically useless. But in the process of deriving his equations, Laplace made a key finding. Tides are driven at only a few specific astronomical frequencies, including the moon, the sun, and the eccentricity of the lunar orbit. Each one of these factors contributes a sine wave of a particular amplitude and phase to the total tide curve. If someone could figure out how to correctly combine these frequency components, well, the tides could finally be predicted. It took nearly a century, but in the 1860s, William Thomson, later Lord Kelvin, took up the challenge. Having completed several voyages to lay the first transatlantic telegraph cable, he developed a fascination with the sea, and subsequently he threw his full scientific effort into measuring and predicting the tides. Tide gauges at the time used a buoy to record the height of the sea onto. Kelvin set out to determine how sine waves with the frequencies identified by Laplace could add together to produce the observed tidal curve. The key was to apply the work of French mathematician Joseph Fourier, who had shown how to decompose any function into a sum of sine waves. Most English scientists were skeptical of the work, but Thomson was enthralled by it. His first paper, published at 17, was a defense of Fourier. While it was straightforward to apply Fourier's analysis to tidal curves, the computation required was enormous. First, divide the tide curve up into short time intervals, and for each interval, multiply the tide level by a sine wave with the frequency of interest. Add up the area of all these rectangles and divide by the total time, and this gives you a single coefficient, the amplitude of the sine wave with this frequency. Then you have to repeat the process for a cosine function with the same frequency. Kelvin found that to make accurate predictions, he actually needed 10 different frequency components. So that is a lot of multiplication and addition to characterize the tides at just one location. For each additional location, you have to perform this analysis all over again. And this is only half the problem. Once you have the amplitudes and phases of the sine functions, you have to add them up to predict future tides. Lord Kelvin spent years analyzing and predicting tides by hand. Then he had a stroke of inspiration. Could you design a machine to carry out these calculations automatically? In Kelvin's words, to substitute brass for brains? The resulting analog computers were in use for nearly a century. They even played a critical role in the outcome of World War II. Kelvin started with the problem of prediction, adding the sine waves together given you know their amplitudes and phases. He knew he could create sinusoidal motion with a device called a Scotch yoke. It extracts one dimension from uniform circular motion. But to make a tide prediction, he needed a way to combine 10 sine waves together. He needed a mechanical analog for addition. Stuck on this problem in 1872, Kelvin boarded a train for a meeting with the main sponsor of his tidal research, the British Association. On the train, Kelvin bumped into a friend, inventor Beauchamp Tower, to whom he explained his dilemma. Tower suggested he use Wheatstone's plan of a chain passing round a number of pulleys, and this was exactly the addition mechanism Kelvin was looking for. By attaching a pulley to each Scotch yoke and running a weighted cord around them, he could mechanically add all of their contributions at once. He scribbled down the entire plan for this predictor machine by the end of the train ride. He pitched it to the British Association and secured funding to build it, all before he returned home. If you knew the relative contributions of different frequency components, Kelvin now had a machine to automate the tedious task of predicting future tides. This was a great leap forward. 4 hours of cranking the handle yielded a full year of tidal predictions. But for many years, the harder half of the problem was still done by hand, breaking apart an existing tide curve into its component frequencies. To automate this step, Kelvin needed a machine capable of multiplying the tide curve times a sine wave and then taking its integral. What would such a device even look like? With his older brother, James Thomson, Kelvin came up with a mechanical integrator. It consists of a ball on a rotating disc. Due to the rotation of the disc, the further the ball is from the center, the faster it spins. If the ball is at the very center of the disc, it doesn't turn at all. And if it's on the left side, it turns in the opposite direction. Now, the motion of the ball is converted into an output via a roller, which moves a pen up or down on the output graph paper. So the way it works is you trace the function you want to integrate with a stylus, and the stylus controls the position of the ball on the disk, and hence its speed of rotation. This is transferred through the roller to the output, which plots the integral of the original function. Now, to decompose a tide curve, we don't just want to integrate the function, we first want to multiply it by a sine wave of a particular frequency. And the way to do this is to make the disk rotate back and forth at that specific frequency. Now the rotation of the ball depends not only on where it is on the disk, but also on how the disk is turning at that instant. You trace the tide curve with the stylus, which moves the ball back and forth on the oscillating disk, and the roller sums up the integral of the tide curve times the sine wave. Simply divide by the total time to get the coefficient. Several of these ball and disk integrators can be connected in parallel, with each disk oscillating at a different frequency, to calculate the coefficients for multiple frequency components at the same time. Kelvin's analog computers revolutionized our ability to predict tides. Tidal curves from anywhere in the world could be turned into a set of sinusoidal coefficients using the ball and disc harmonic analyzer. And the resulting sinusoids could be added together to predict future tides using his Scotch yoke pulley machine. Kelvin's harmonic analyzers were the basis for a landmark analog computer called the differential analyzer, and his tide predicting machines were used well into the 1960s. In fact, they were later overhauled to include 26 frequency components and used to plan the Allied invasion on D-Day. The Germans expected any invasion to come at high tide to minimize the time Allied soldiers would be exposed on the beaches, so they installed millions of obstacles that would be underwater by mid-tide, many with explosive mines attached. But the Allies spotted the obstacles and changed tack. Instead, they planned to begin the invasion at low tide. This would allow demolition teams to first clear channels through the obstacles. Then the main forces could come through those gaps as the water rose. This would also give landing craft enough time to depart without getting beached. The low water times were different at the 5 landing beaches by over an hour, so the invasion times were staggered according to the tide predictions. This wasn't the only use of analog computers in World War II. Dive bomber aircraft would plummet out of the sky directly toward their targets at up to an 80-degree angle, and their rapid descents made them very difficult to shoot down. So the US began searching for devices to automatically aim guns at dive bombers. Most of the proposed solutions fell into one of two categories. Some were analog machines like Lord Kelvin's, others were essentially fast calculators. Mechanical calculating machines like the abacus had been around for millennia, but they were far too slow to respond to dive bombers. These new calculating machines sped things up by using electrical pulses. The committee considered naming these devices after the pulses they used, but member George Stibitz proposed a more general name, digital, because these machines operated on numbers themselves, or digits. And this is the origin of the term digital computer. But digital would have to wait. Of all the proposals, an innovative analog machine from David Parkinson won out. At Bell Labs in New York, Parkinson had been working on a device to chart telephone data called an automatic level recorder. It used a variable resistor called a potentiometer to control the motion of a pen. One night, after hearing reports of the harrowing Allied evacuation of Dunkirk, Parkinson had a dream that he was on the front lines. I found myself in a gun pit with an anti-aircraft gun crew. A gun there was firing occasionally, and the impressive thing was that every shot brought down an airplane. After 3 or 4 shots, one of the men in the crew smiled at me and beckoned me to come closer to the gun. When I drew near, he pointed to the exposed end of the left trunnion. Mounted there was the control potentiometer of my level recorder. When he woke up, Parkinson realized the device he was building to control a pen could be scaled up to control an anti-aircraft gun. He shared this idea with his supervisor, and after receiving approval from the military, they set out to make Parkinson's dream a reality. Researchers at Bell Labs had recently invented an analog electrical device called an operational amplifier, or op-amp. It could perform mathematical operations with voltages, like addition and multiplication. They used these op-amps to create an analog computer that could solve the ballistics equations for anti-aircraft guns. Using radar and optical sights to obtain the speed, altitude, and direction of enemy planes, the M9 gun director, as the computer was called, could rapidly calculate the correct trajectory and fuse setting. Potentiometers were used to ascertain the direction the gun was pointing. This was not the first electric analog computer, but it was an important one. In World War I, it took an average of 17,000 rounds to take down a single airplane. In 1943, after the invention of the M9, it took an average of only 90. During the war, the US invested big in analog computers. If you break down their total military budget, the third largest single expense was the development and production of an incredibly complex mechanical analog computer called the Norton bomb sight. Unfortunately, they didn't get their money's worth. Designed by the eccentric Dutch engineer Carl Norton, the Norton bomb sight was built to enable high-precision airborne bombing. It implemented 64 different simultaneous algorithms, including one that compensated for the rotation of the Earth as the bomb fell. The Norton was one of the most closely guarded secrets of the war. To prevent the technology from falling into enemy hands, American bombardiers. A plane plummets out of the sky. A speedrunner inexplicably jumps to a higher platform.
What the?
And an election recount is triggered, all because of the same invisible phenomenon that permeates the universe. On May 18, 2003, voters in Belgium went to the polls. In many regions, voting was done on a computer, something the Belgians had been experimenting with for over a decade. But the system had a backup. Each voter would insert a magnetic card into the machine and make their selection on screen. Their vote was saved both to the computer and the magnetic card, which they dropped into a box for redundancy. Late that night, as the votes were being tabulated, one of the election officials detected a problem with the results from Schaerbeek, a municipality in central Brussels. Maria Vindevogel, a little-known candidate with her own party, received more votes than was mathematically possible. They knew this because of the way the preferential voting system works. So they took out the magnetic cards and started a recount. One by one, they fed each of them through the machines again. And after several hours, the recount was complete. The vote totals for every candidate were exactly the same as before, except for Maria Vindevogel. In her case, the recounted number of votes was less than the original by 4,096. So what went wrong? How had her original tally been inflated by over 4,000 votes? Computer experts were brought in to run extensive tests on the software. They combed through the code but could find no bugs. They got the computer that had made the initial erroneous tally and tested the hardware again and again, but they could not replicate the error. Everything about the hardware seemed to be in perfect working order. And this left only one possible explanation, and it is seriously weird. The clue comes from the excess number of votes Vindevogel received, 4,096. Computers work using binary, strings of zeros and ones, each corresponding to a power of 2. So somewhere inside the computer tabulating all the votes was a string of bits representing the number of votes Maria received. It started the day all zeros, and then as each vote for her came in, it would increment by 1. Physically, this is done by turning on a transistor for 1 and turning it off for 0. What's remarkable about the number 4096 is that it is exactly a power of 2, 2 to the power of 12. That is the 13th bit. So for Maria Vindevogel to receive an extra 4,096 votes, only one thing needed to happen. The 13th bit had to flip from a 0 to a 1. But why would that happen? Computers work precisely because bits don't flip unless we want them to. Or do they? Looking into the problem, Belgian investigators found reports of similar issues from big computer companies starting in the 1970s. In 1978, Intel reported some strange errors popping up in their 16 kilobit dynamic random access memory, or DRAM. Ones would spontaneously flip to zeros with no apparent cause. The problem turned out to be the ceramic packaging the chip was encased in. With the demand for semiconductor packaging skyrocketing in the 1970s, a new manufacturing plant was constructed on the Green River in Colorado. Unfortunately, this site happened to be just downstream of an old uranium mill. Radioactive atoms made their way into the river and then into the ceramic packaging for Intel's microchips. Intel scientists investigating the problem found that even trace amounts of uranium and thorium in the ceramic were sufficient to cause problems. In their DRAM, memory was stored as the presence or absence of electrons in a semiconductor well. The alpha particles emitted by uranium and thorium were energetic and ionizing enough to create electron-hole pairs in the silicon. If an alpha particle struck in just the right place, it could create a large number of free charge carriers, causing electrons to accumulate in the well, flipping a 1 to a 0. This is known as a single event upset, a type of soft error. The error is soft because the device hasn't been damaged. The bit has changed, but you could erase it and rewrite it with no problems. Investigators exposed the chips to alpha emitters with different levels of activity, and just as you'd expect, they found the number of bit flips directly correlated with the number of alpha particles the chip had been exposed to. The reason this problem was identified in the 1970s was because chip components had been miniaturized to the point where a single alpha particle could produce enough charge to flip a bit. Immediately, these findings attracted a lot of attention. Before the paper was published, it was widely circulated in the industry, and as a result, chip manufacturers were a lot more careful to avoid radioactive materials when producing their microchips and packaging. Therefore, the bit flip that gave Maria Vindevogel 4,096 extra votes wasn't caused by natural radioactivity in the computer. So where did it come from? After Henri Becquerel discovered radioactivity with uranium in 1896, scientists sought a way to measure it. How radioactive were different materials? And one way to do this is with a gold leaf electrometer. When it's charged, the leaf is repelled, and you can measure the amount of charge by the angle of the leaf. Now, if ionizing radiation enters the chamber, it rips electrons off air molecules, creating positive and negative charges. Opposite charges are attracted to the leaf, discharging it over time. The higher the level of ionizing radiation, the faster the device discharges. In 1910, Theodore Wolff took his electrometer to the top of the Eiffel Tower. Since radioactivity was found in the soil and rocks of Earth, he expected that 300 meters up, the radiation would be just a few % of the ground radiation. Instead, he found only a slight decrease. In 1911, Austrian physicist Victor Hess decided to take this experiment further. Literally. He loaded electroscopes into the basket of a hydrogen balloon. In his first 2 flights, he observed the same thing as Wolff. Up to an altitude of 1,100 meters, both trips revealed no fundamental change in radiation compared to the values observed on the ground. But the next year, he conducted 7 balloon flights, up to an altitude of 5,200 meters. And here, he discovered something remarkable. While there was an initial drop in radiation for the first several hundred meters, above 1 kilometer or so, the level increased with increasing altitude. At his maximum height, the level of radiation was several times greater than it was on the ground. The radiation appeared to be coming not from the Earth, but from the sky. Hess scheduled one of his balloon flights during a solar eclipse, and as the moon passed in front of the sun, he carefully watched his instruments. But the readings were unaffected. Even with the sun half covered, the level of radiation was the same. Since no influence of the eclipse on the penetrating radiation was noted, we conclude that even if a part of the radiation should be of cosmic origin, it hardly emanates from the sun. Victor Hess had discovered cosmic rays, high-energy radiation from space. But what were these rays exactly, and where were they coming from? Well, today we know they aren't electromagnetic rays as many suspected, but particles. Around 90% are protons, 9% are helium nuclei, and 1% are heavier nuclei. Some of them are from the sun, but they have comparatively low energy. High-energy cosmic rays, moving very close to the speed of light, come from exploding stars, supernovae, in our own galaxy and in others. And the highest energy particles are thought to come from black holes, including the supermassive black holes at the centers of galaxies. But it's hard to pin down exactly where cosmic rays come from because, as charged particles, they're deflected by magnetic fields in space, so they can wind their way through the universe for billions of years. A cosmic ray detected on October 15th, 1991, had an energy of 51 joules. That is a single subatomic particle with the energy of a baseball going 100 kilometers per hour. For obvious reasons, it was dubbed the OMG particle. But primary cosmic rays like these don't make it down to Earth's surface. Instead, they collide with air molecules around 25 kilometers above the ground and create new particles, like pions. These collide and decay into other particles like neutrons, protons, muons, electrons, positrons, and photons, which in turn collide with other air molecules in one long cascade. So from a single primary cosmic ray comes a shower of particles streaming towards the Earth. It is one of these particles that investigators suspect struck a transistor in a computer in Belgium, flipping the 13th bit from a 0 to a 1 and giving Maria Vindevogel 4,096 extra votes. But how often do things like this happen? In 1911, Charles Wilson made it possible to see the cosmic rays all around us when he perfected his cloud chamber, an enclosure with supersaturated water or alcohol vapor. When a cosmic ray passes through the chamber, it ionizes the gas, causing vapor to condense into tiny droplets on the ions, revealing the path of the particle. Alpha particles, helium nuclei, leave short, thick tracks, while beta particles, electrons, leave long, skinny trails. In 1932, Carl Anderson identified a trail that looked like it was made by an electron, but in the applied magnetic field, it curved in the wrong direction, implying it had a positive charge. Anderson had found the anti-electron, or positron. It was the first confirmed sighting of antimatter. 4 years later, also using a cloud chamber, he discovered the muon, again in cosmic rays. For his discovery of the positron, Anderson was awarded the Nobel Prize in Physics in 1936. He shared the prize with Victor Hess, the man who discovered cosmic rays in the first place, invisible particles that affect our lives in ways most of us are oblivious to. This is possibly the rarest thing to ever happen in a video game. In 2013, user Dota Teabag was speedrunning Super Mario 64 on the console. In the level Tick-Tock Clock, he suddenly upwarps onto a higher platform.
What the?
Did you get invisible walls?
What?
Please say you got invisible.
No, that was the craziest thing I've ever seen, though.
The move shaves off a few seconds, and it seems like a newly discovered glitch in the game that could give speedrunners an edge. User PanandCook12 put out a $1,000 bounty for anyone who could replicate the upwarp. But so far, after 6 years, no one has been able to. The best explanation anyone can come up with is that a cosmic ray caused the glitch. It's been shown that a single bit flip in the first byte of Mario's height coordinate could have caused the effect. On the main level, the byte was 11000101, but if you flip the last 1 to a 0, it changes his vertical position. And just by chance, this new height coincides with the higher floor. PanandCook12 wrote a script to manually flip the bit at the right moment and was able to achieve the same upwarp. This is a particularly visible bit flip, but the truth is, cosmic rays are triggering bit flips all the time.
An upset there, or transient there, can alter the function of these devices, and we call that a single event functional interrupt. So an entire process can hang. So a blue screen of death that you get might actually have been a neutron or whatnot.
When people see the blue screen of death, could that be caused by a cosmic ray?
Absolutely.
These days, there are a number of ways computer chips are made resilient in the face of bit flips, like error correction code or ECC memory. But you can't totally prevent bit flips from happening. In 1996, IBM estimated that for each 256 megabytes of RAM, 1 bit flip occurs per month. And the main culprit seems to be neutrons created in the shower of particles from cosmic rays. Starting in 2009, Toyota recalled millions of vehicles due to the problem of unintended acceleration.
We were in the fast lane driving at about 70, and he said that the car was continuing to accelerate, and he couldn't bring it to a stop.
Many speculated that cosmic ray-induced bit flips in the electronic control system were the cause. So much so that NASA was called in to help with the investigation. But it turns out cosmic rays were probably not the culprit. NASA identified as the main causes sticky accelerator pedals, poorly fitted floor mats, and most commonly, drivers pushing on the accelerator thinking it was the brake. But cosmic rays have caused crashes of supercomputers, especially at higher elevations. Los Alamos National Labs, located 2,200 meters above sea level, is constantly dealing with neutron-induced supercomputer crashes. So the software autosaves frequently, and neutron detectors have been installed throughout the facility. If you go even higher, like climbing up to cruising altitude in a plane, you can see the radiation from cosmic rays increasing on a Geiger counter. To 0.5 microsieverts per hour at 18,000 feet, up to 1 microsievert per hour at 23,000 feet, over 2 microsieverts per hour at 33,000 feet, and over 3 microsieverts per hour at even higher altitudes and towards the poles. At cruising altitude, this increases the chance of a single event upset by 10 to 30 times. This isn't critical if it happens in your laptop, but what if it occurs in the flight computer? On October 7th, 2008, an Airbus A330 took off from Singapore to Perth. Just over 3 hours into the flight, the plane suddenly pitched down, diving 200 meters in 20 seconds. Inside the plane, everyone experienced negative 0.8 Gs of acceleration. It would have felt like the plane had flipped over.
The G-force was enough, even with our 3-point harness, to lift us both out of the seat and push us forward as well.
Minutes later, the plane dropped another 120 meters. 119 people on board were injured, many from bumping their heads into the ceiling. So the pilots decided to make an emergency landing in Learmonth. In the investigation that followed, the fault seemed to occur with the first Air Data Inertial Reference Unit, or ADIRU for short. This computer supplies critical data like airspeed, angle of attack, and altitude. The way it supplies each of these pieces of information is in a 32-bit binary word. The first 8 bits identify the type of information, and bits 11 to 29 encode the actual data. What seems to have happened is that a bit flip in the first 8 bits meant altitude information was mislabeled as angle of attack information. Inside the cockpit, alarms went on for overspeed and stall simultaneously, something that should be impossible. But the plane nosed down sharply to correct what it thought was a stall, throwing passengers and crew into the ceiling. Investigators looked into software bugs, software corruption, a hardware fail, physical environment factors, and electromagnetic interference. But each of these possibilities was found to be unlikely based on multiple sources of evidence. The other potential triggering event was a single event effect resulting from a high-energy atmospheric particle striking one of the integrated circuits within the CPU module. One of the challenges with single event upsets is that they are soft errors. They don't leave a trace. But interestingly, the Airbus A330 was built in 1992, when there were no specific regulatory or aircraft manufacturer requirements for airborne systems to be resilient to single event effects. With the space shuttle, redundancy was built in from the start. For navigation and control, there were 4 computers simultaneously running identical software. If one computer had a soft error, the other 3 would overrule it. And using this setup, they could also track the frequency of bit flips. On one 5-day mission, STS-48, there were 161 separate bit flips. Above the atmosphere, cosmic rays are so energetic, sometimes you can even see them.
Once in a while, you have your eyes closed and you're not asleep yet. And if you wait a little while, you occasionally will see a flash of light. And we think it is heavy particles or individual bursts of energy coming from radiation that are either going through the eyeball itself or going through the optic nerve. And the way that your body registers radiation going through it is amazingly enough by showing you a little flash in one of your eyes, just to remind you that you are subject to the radiation of not only our sun, but every star of the universe that is radiating at you. I picture back to the first astronauts who must have closed their eyes and seen that radiation and going, I'm not going to tell anybody about this because no one's told me about it. I'm not talking. And I can just imagine the first 2 guys that said, hey, sometimes I see flashes of light. Do you see flashes of light? And then it's, oh, we all see flashes of light. Oh, okay. Well, that's all right then.
For missions to other planets, protecting electronics is critical.
If a single bit of information controls a critical function on your spacecraft, let's say your thrusters, and that goes from a 1 to a 0, from a on to off, or vice versa, you could lose the mission.
That's why the computer on the Perseverance rover that just landed on Mars is 20 years old. It's a PowerPC launched in 2001 with only 256 megabytes of RAM and 2 gigabytes of flash storage. But it is radiation hardened, meaning the design, materials, circuits, and software are built to withstand 40 times the radiation of an ordinary computer. It's been used on over a dozen space missions going back to 2005.
In fact, when we first started doing the PowerPC testing years ago, the way we did it, we just simply stuck an operating system processor in a beamline where we generate these particles on the planet and look for blue screens of death. You can kind of figure out what's going wrong and try to undo that so you don't get to the blue screen of death, because a spacecraft that gets into that mode is basically unrecoverable.
As the Voyager 1 spacecraft departed the solar system, one of the ways we could tell was by an increase in the flux of cosmic rays it experienced. Although on Earth the particles streaming from the sun and the solar wind are a source of radiation, further out, these same particles maintain a protective bubble, the heliosphere. It helps deflect and slow cosmic rays from interstellar space, protecting the solar system from ionizing radiation. But the sun has an 11-year activity cycle, so this protection fluctuates. The flux of cosmic rays on Earth is much lower when the sun is active than when it's dormant. In the history of our planet, cosmic rays may have played an even larger role, flipping bits not in electronics, but in the genetic codes of living organisms, providing some of the variation on which natural selection acts. Maria Vindevogel is now a member of the Belgian Chamber of Representatives, elected by people, not a particle. But her story is a reminder of the zillions of particles winding their way through the universe for millions or billions of years, one of which might, at any moment, change your life by passing through a tiny transistor and crack. This video was sponsored by KiwiCo. More about KiwiCo at the end of the show. I know what you're thinking. Clickbait! No one has measured the speed of light? That's ridiculous. The speed of light is exactly 299,792,458 meters per second. We are so sure of it that since 1983 we've actually used the speed of light to define how long a meter is. It's just the distance light travels in a vacuum in 1/299,792,458 of a second. That definition ensures that the speed of light is exactly this number, no decimals. But hear me out. In this video, I will prove to you that light may never actually travel at this speed. And I can say that because no one has actually measured it. We can't measure the speed of light the same way we measure the speed of anything else.
I think we're recording everywhere. What are we doing?
This is a video about measuring the speed of stuff.
Okay.
Tell me about how you measured the speed of the baseball fired out of your cannon.
Well, to get the speed of the baseball, you need to know two things. You need to know the distance between 2 points, and you need to know the time that it takes the baseball to travel between those points. So basically, we took distance divided by time, and that's the speed of the baseball. And in our case, we were shooting with a high-speed camera. So you basically just count the frames, and then your clock is internal. Oh, you're going relativity. You're going to do something weird, aren't you?
You saw it coming. I can't believe it.
Oh, man.
The thing I want to ask you about is the speed of light.
Okay.
Could you measure the speed of light like this? Imagine you have a laser that can fire a beam through a perfect vacuum for 1 kilometer. Start a timer the instant you fire the laser beam, and then exactly when it hits the end, stop the clock. Except, how do you know when light reaches 1 kilometer if you and the clock are at the starting point? Okay, so you need 2 clocks, one at the laser and one at the end, which stops automatically when it detects the laser light. But now, how do you make sure your 2 clocks are synchronized? Well, you could connect them via a wire and send a pulse from one to the other, but that pulse will travel at the speed of light, so it will arrive with a time delay. You might think you can just subtract that time delay, but it is equal to the time it takes for light to travel 1 kilometer. That's what we don't know and are trying to measure. Okay, new plan. Start with the clocks together and sync them up first, and then send one of the clocks down to the end. Now, what could possibly go wrong? Well, I'll tell you. The clock at the finish line was moving with respect to the one at the start, and special relativity tells us moving clocks tick slow relative to stationary observers. So by the time the clock reaches 1 kilometer, it will no longer be in sync with the clock at the start. Can I tell you the only solution to this problem? Ditch the second clock. Put a mirror at the end to reflect the light back, and use a single clock at the start to time the full 2 kilometer round trip.
Wasn't this actually done before? He was on a mountain and there's a wagon wheel with a lantern and there's something like a mirror on the other side of the mountain. I've always wanted to do this.
So, that sounds a little like how the speed of light was first experimentally measured by Hippolyte Fizeau in 1849. He shone a beam of light between the teeth of a rapidly spinning gear to a mirror up on a hill 8 kilometers away. And then by increasing the speed of the gear, he reached a point where the reflected light passed through the next gap on the gear, and so it was observed. So he measured the speed of light to be 313,000 kilometers per second, which is within 5% of the presently accepted value. So someone has measured the speed of light. Or have they? What has been measured is the round trip or two-way speed of light, but no one has measured the one-way speed of light. One thing I'm going to throw at you, and I'm just gonna come out and tell you. It's like, what if the speed of light in this direction is different from the speed of light in this direction?
Then that sounds like a Veritasium video.
The question is, could you figure it out? The kind of crux of this problem is that the only way people have managed to measure the speed of light is for a round trip. No one's ever managed to measure the speed of light in just one direction. It's possible that the speed of light is half of c in one direction and then instantaneous on the return journey.
What?
That's possible.
Are you serious?
Think about communicating with an astronaut stranded on Mars. Let's call him Mark. We send out a signal and get a response 20 minutes later. So we imagine our signal takes 10 minutes to get there, and the reply takes 10 minutes to come back. But it's possible that our message took all 20 minutes to get there, and the reply came back instantaneously. There's no way we could tell the difference between these two scenarios. But why would the speed of light be different? Well, it's possible that there is some preferred direction through space-time. I mean, our universe has a lot of symmetries, but there is also some asymmetry. For example, why is there so much matter relative to antimatter? And physicists have worked out internally consistent theories of physics in which the speed of light is different forwards and in reverse. The speed of light could vary by just a few percent, up to, at the extreme, going c/2 in one direction and infinitely fast in the other direction.
Okay, so let me figure this out. So, yeah, I kind of don't believe you. I don't believe you that light is a different speed in one direction but in the other. But I know you well enough to know that you wouldn't call me and put a camera on me unless you knew you were right. And that's what scares me about this conversation. That scares me.
Now, you might think it is just simpler that light should travel at the same speed in all directions, but the truth is that is a convention rather than an experimentally verified fact. Einstein himself pointed this out in his famous 1905 paper on the electrodynamics of moving bodies. He spends the first couple of pages on the problem of synchronizing clocks at different locations, A and B. And he says, there is no way that we can meaningfully compare the times they measure unless we establish by definition that the time required by light to travel from A to B equals the time it requires to travel from B to A. He's essentially defining that the speed of light in opposite directions is the same. And he puts by definition in italics to remind us that this is only a convention. It's known as the Einstein synchronization convention. So the idea that the speed of light is the same in opposite directions, as Einstein would later write, is neither a supposition nor a hypothesis about the physical nature of light, but a stipulation that I can make of my own free will to arrive at a definition of simultaneity. That sounds a lot more subjective than how I think most people would imagine the speed of light is defined.
Dude, this is hardcore. I've never thought about this.
I didn't think about this before either. I always assumed that when we said the speed of light is c, we meant the one-way speed of light. There's no way to define the one-way speed of light. So the only thing we can really define is the two-way speed of light.
Just look at the way Einstein defines c. It's for the round trip from A to B and back.
I don't know if you saw in your physics classes, but whenever there was a light clock, it would always bounce the light up and then back. You would never see a light clock just bounce light one way. And this is why. The only thing we can be certain is constant for all inertial observers is the two-way speed of light.
For over 100 years, scientists have tried to find a way around this, to measure the one-way speed of light by itself. Here is a paper published in the American Journal of Physics in 2009 that claims to measure the one-way speed of light. And here is the paper debunking this study, pointing out that these authors were actually measuring the two-way speed of light. But I'm imagining you might have some ideas for how to measure the one-way speed of light, so let's go through some of them. I mean, can't we just use a high-speed camera that shoots at 1 trillion frames a second so we can actually see light passing through an object? The problem is, you're not only seeing the light pass through the object, you're also seeing it bounce back to the camera, measuring the two-way speed, not one-way.
Here you go. Get a spool of fiber optic cable, I don't know, like 186,000 miles, and you could shine the light here, and you have the other end of the fiber here, and you could shine here and then wait and see the delay, see if it's 1 second later over here.
The thing is, like, that fiber's going around and around and around, so it could be that when the light goes this way over the top of the loop, it goes slower, and then when it goes on the bottom, it goes faster. It all averages out in the fiber, and you're essentially getting lots of round trips in that fiber. So you're never getting a one-way.
What if you center a synchronizing device between your two clocks and send out simultaneous pulses? Well, if the speed of light is the same in both directions, this perfectly synchronizes your clocks. But if the speed of light is different in each direction, one of the clocks will be ahead of the other, and it will be ahead by just the right amount, so that when you measure the speed of light, you'll find the value to be c, even though that was not the speed the light was traveling. This is the same reason GPS synchronized clocks won't work. The whole GPS system is based on the assumption that the speed of light is the same in all directions. If the speed of light is different in different directions, the light pulses from satellites will travel at different speeds, so the clocks won't be properly synced. By that I mean they will always measure c for the one-way speed of light, whether it is or isn't. How about starting with synchronized clocks in the middle and moving them apart with equal and opposite speeds? That way the time dilation for each clock will be the same and they'll still be synchronized when they reach the endpoints. But again, this only works if the speed of light in each direction is the same. If the speed of light depends on direction, then so does time dilation. You might think you could move the clocks really, really slowly so that time dilation is negligible. But if the speed of light is different in different directions, you can't just use the standard formula to calculate what that time dilation would be. I mean, it could be a lot worse than you think. So the reality is we're stuck. We need synchronized clocks to measure the one-way speed of light, but we need to know the one-way speed of light in order to synchronize our clocks. Now this might sound like just an academic concern, so I want to go through an example to illustrate just how differently the universe works if the speed of light is not the same in all directions. Let's say on Mars, Mark is trying to synchronize his clock with the Earth. At noon, Mission Control sends out a message that says, "This signal was sent at exactly 12 o'clock. When Mark receives this message, he uses the Einstein synchronization convention to set his clock. He knows the round-trip time delay is 20 minutes, so he assumes the signal must have taken 10 minutes to reach him. He programs his clock to 12:10 p.m. and sends a return message. This reply sent at 12:10. The message is received on Earth at 12:20 p.m., so both parties know the synchronization was successful. When the clock reads 12:20 on Earth, it simultaneously reads 12:20 on Mars. But now consider what happens if the speed of light is not the same in both directions. Let's say it is c/2 from Earth to Mars, and then instantaneous from Mars back to Earth. No one knows this, of course, so they continue to use the Einstein convention. The message is sent from Earth, but now it takes a full 20 minutes to reach Mars. But Mark doesn't know this, and as before, he assumes the signal took 10 minutes to reach him, so he sets his clock to 12:10 p.m., even though on Earth it is now 12:20. Mark then sends this reply sent at 12:10 p.m., which is instantaneously received on Earth at 12:20 Earth time. The experience for the two communicators is the same. The same messages were received with the same local time delays, but their clocks are out of sync by 10 minutes. What they think is the same moment for the other observer actually isn't, and there is no way they can ever recognize or correct this error. Imagine if someone on Earth immediately responded, "How long did this message take to reach you? It's now 12:20. Well, the message would take 20 minutes to reach Mars, but due to the clocks being
a point. Next, cable wire is an example of point, line, or plane. Wire, that is a line. How about number 4, top of a box? Yes, it is a plane. Number 5, cover of a book. About the cover, is it a plane? And last, a cloth line. Yes, it is a line, of course. Okay, we're done in letter A. Now let us proceed in letter B. Direction: draw a figure to illustrate each relationship. This time we're going to draw a figure. Now number 1, collinear points P, T, and S lie on line P. So we have a line P, so we're going to draw a line P. This is a line P, and we have collinear points. We have 3 points. We will name it as P, T, and S. So this will be your answer. Okay. Now, can you try number 2? Coplanar points M, N, and Q lie in plane T. Can you draw the figure, then label the points? Now let's check your answers. We have plane T, so we have plane T. Let's say this is our plane. We'll name it as T. And we have coplanar points. Inside our plane T, we have the 3 points, M, N, and Q. This will be your answer, or the answer in number 2. Did you get the same answer? Next, number 3. Line XY contains point E, but not point G. So we have a line XY, so we need to draw the line. Let's say this is our X and Y, and the line contains point E. So let's say we have point E here, but not point G. So G will be in this part, or or you can write G in this one or in this area. Okay. And number 4, line VW lies in a plane H. So we have H, plane H. Let's say this is our plane H. Then a line lies in plane H. So we have line VW. And now we're done in our activity A and B. Did you understand the basic undefined terms in geometry? Thank you for watching Senior Pablo TV.